Cambridge IGCSE, Paper 3, October-November 2014. Number 1. Figure 1.1 shows the distance time graph for three different objects A, B, and C. Describe the motion of each of the objects A, B, and C by selecting an appropriate description from the list below. For A and B, distance is increasing. For C, the distance is remaining constant, so C is remaining at a fixed position. So if this is O, the origin, and C is at a fixed position, so the distance between them is fixed, this means that C is stationary. In B, the variation is a straight line, so D is increasing at a constant rate, and the rate of the distance is actually the speed, so constant speed. Now A, distance is also increasing, and the rate of this increase is increasing. It's getting steeper with time, approaching the vertical. In this case, the gradient of the line is increasing, which means that the speed is increasing, since the speed is the gradient of the distance. So we have increasing speed. Part B, figure 1.2 shows the speed time graph, speed now with time, for three more objects D, E, and F. Describe the motion of each of the objects D, E, and F by selecting the appropriate description from the list below. For F, the speed is constant since the line is horizontal, so the value of the speed is remaining the same. For F, constant speed. For E, it's increasing and straight line, which means constant gradient. And for V, the gradient is the acceleration, so we have constant acceleration. And for D, also the line is getting steeper and steeper, approaching the vertical, so its gradient is increasing, which is the acceleration. So the speed is increasing, and also the rate of this increase is increasing, which is the acceleration. Part C, figure 1.3 shows a person bungee jumping from a bridge. The person is attached to a long elastic rope. Part 1, in 1.5 seconds, the speed of the jumper increases from 0 initial speed to 10.5 meters per second. Find the acceleration, which is actually the change of speed, so 10.5 minus 0 over the time taken, which is 1.5, and so the answer will be 7 meters per second squared. At one point during the fall, she reaches her maximum speed. State the acceleration at this point. When the speed is maximum, so it's a constant value, and this means that the acceleration will be 0 meters per second squared. No acceleration. What can be said about the forces acting at this point? Since the acceleration is 0, we know that the force resultant is equal to ma, and during its motion it has only two forces, which are air resistance or upward force, and of course the gravitational force. So these forces now at this specific point of the maximum speed are equal and they cancel each other, so the resultant force is 0 and the upward force is equal to the downward force. So we can say F upward, which is this one, is equal to F downward, which is this force, or air resistance is equal to the weight, or mg. Number 2, a diver climbs some steps onto a fixed platform above the surface of the water in a swimming pool. He dives into the pool Figure 2.1 shows the diver about to enter the water. The mass of the diver is 65 kilograms. The platform is 8 meters above the surface of water. Calculate the increase in gravitational potential energy of the diver when he climbs up to the platform. From this position to this position, his height increased by 8 meters, and so his gravitational potential energy variation is equal GP increase is equal mass multiplied by gravity multiplied by height equals 65 multiplied by 10 multiplied by 8 meters, and the answer is 5200 joules. The speed with which the diver hits the surface of water ignore the effects of air resistance. At this position, he has kinetic energy is equal to 0 and gravitational potential energy is equal to 5200 joules. At this position now, he has 0 potential energy, so all this energy is converted into kinetic. Kinetic energy is equal to half mv squared, and it's equal to this value. So kinetic energy gained is equal to gravitational potential energy lost. This means that half mv squared is equal 5200 joules, and so v squared is equal to multiplied by 5200 divided by the mass, which is 65, and v is equal to the square root of this answer, which is equal to 12.6 meters per second. Part B. In another dive from the same platform, the diver performs a somersault during the descent. He straightens and again enters the water as shown. Discuss whether the speed of the entry of water is greater than, less than, or equal to the speed calculated in A2. I. Ignore any effect of air resistance. Actually, whatever he does while falling down, kinetic energy gained, as we said, is equal to the gravitational potential energy lost. And since this quantity is the same, GPE lost is the same. Why? Because he's falling the same height. And we mentioned that gravitational potential energy is equal to mass times gravity multiplied by the height. So mass is the same, gravity is the same, it depends only on the height. Since the height is the same, so gravitational potential energy is the same. So kinetic energy gained is also the same. Therefore, he reaches with the same speed. Number 3. Figure 3.1 shows an oil can containing only air at atmospheric pressure. Atmospheric pressure is 1.0 times 10 to the power 5 pascals. The pressure of air in the can is reduced by means of a pump. The can collapses when the pressure of air in the can falls to 6000 pascals. Explain why the can collapsed. Actually, the can was maintaining this shape because the pressure of the air molecules inside is equal to the pressure of the air molecules outside. So this will make kind of a balance, and it remains in this shape. Now when air molecules are taken out, so now the pressure inside is smaller than the pressure outside, and the reason of this will be that the external pressure will dominate the internal pressure and will compress the can. So the force outside, or the pressure exerted outside, is greater than the pressure inside. For this reason it collapses. The surface area of the can is given 0.12 meters squared. Calculate the resultant force on the face X. When the can collapses means that the pressure is now 6,000 pascals. So pressure is equal to force divided by area, and so force is equal to pressure multiplied by area. The resultant pressure is the external pressure, which is atmospheric, minus the internal pressure, which is this. So pressure is equal 10 to power 5 minus 6,000 multiplied by 0.12 meters squared, and the result will be 11,280 newtons. B. Mercury is poured into U-shaped glass tube. When water is then poured into one of the limbs of the tube, oil is poured into the other limb until the surfaces of the mercury are at the same level in both limbs. Figure 3.2 shows the result. State a condition that must be true in order for mercury surfaces to be at the same level in both limbs of the tube. Any 2 points at the same height should have the same pressure. So the pressure above this limb should be equal to the pressure above this limb, and this means that pressure of oil is equal to pressure of water. So pressure of oil must be equal to pressure of water to keep them at the same level. The height of the water column is 0.25 meters. The height of the oil column is 0.32 meters. The density of water is given 1000 kilometers cubed. Calculate the pressure exerted by water on the surface of mercury. P is equal density multiplied by gravity multiplied by the height, which is equal to density of water 1000 multiplied by 10, gravity multiplied by 0.25 meters, the height of the water column, and so the answer will be 2500 pascals. Now the density of oil, pressure of oil, is equal to rho oil, which is not given, multiplied by gravity multiplied by height. Pressure of oil is equal to pressure of water, so 2500 is equal to rho oil multiplied by 10 multiplied by the height of oil column, which is equal to 0.32 meters, and so rho is equal to 2500 divided by 10 multiplied by 0.32, and the answer will be 781 kilograms per meters cubed. Number 4 now. Figure 4.1 shows some of the apparatus that a student uses to determine the specific heat capacity of aluminium. We have electric heater inside aluminium block, which is insulated in an insulating container, and 2 connections to electric circuit from the heater, and thermometer immersed inside. State measurements that the student need to make, including those from the electric circuit. For each quantity measured, state the symbol. We know that the heat energy supplied is equal to mass multiplied by specific heat capacity multiplied by change of temperature delta theta. So specific heat capacity C is equal to E divided by M multiplied by delta theta. So C is equal energy, which is equal over here to the electrical energy supplied to the heater. So power times time over mass multiplied by delta theta, or theta change of temperature is theta final minus theta initial, and so C is equal electrical power, which is equal V times I, voltage multiplied by current, by T over mass multiplied by final temperature minus initial temperature. So the quantities which we have to find is first M, which is the mass of the block, then theta I, initial temperature, theta F, final temperature, 1 mark for these two, 1 mark for the mass, then T, which is time, also 1 mark for it, time of heating, and finally V, voltage of the source, I, current, both of them for finding the power, so 1 mark for both of them. Part B, use your symbols from A to complete the formula used to determine the specific heat capacity. We already wrote it. It's equal E, or voltage multiplied by current multiplied by T, divided by mass, change of temperature, theta final minus theta initial, or theta 2 minus theta 1. Another student performs the experiment without using insulation. He obtains a higher value to C. Explain why this student's measure lead to a higher value. Without insulation, the voltage provided is the same, current in the circuit is also the same, time can be the same, and so for the mass, but the difference will be in theta 2, because without insulation some of the heat will be liberated outside, and so it will not reach theta 2, it will rather reach a temperature less than it, so this quantity all decrease, and because the denominator gets smaller, so the specific heat capacity gets bigger. So we can write because heat loss or energy loss increases. Number 5. Two types of seismic waves are produced by earthquakes. They are called P waves and S waves. P waves are longitudinal and S waves are transverse. Explain what is meant by the terms longitudinal and transverse. We say that the wave is longitudinal when the vibration of the particles or molecules is in the same direction of the wave. In transverse, the vibration of the particles is perpendicular to the direction of the wave. So just we remove same and we put perpendicular. Vibration of particles is perpendicular to the direction of the wave. State another example of a longitudinal wave, sound wave. Compression wave of a spring. We can also make longitudinal wave by compressing the spring. So compressions and rarefactions will occur. Transverse wave also can be created in a spring, but not by compressing it, by moving it up and down. Another example of transverse wave are the waves in water or electromagnetic waves, but we have to specify. In case we said electromagnetic waves, we should say a kind of magnetic wave like visible light, like X-ray, like microwaves, any kind of electromagnetic waves. Or a wave of rope can be considered as transverse wave. 3i. A seismic wave has a speed of 7.2 kilometers per second and frequency of 30 Hz. Calculate the wavelength. Lambda is equal to speed divided by the frequency, 7.2 divided by 30, and so the answer will be 0.24 kilometers or 240 meters. B. Figure 5.1 shows an electric bell ringing in a sealed glass chamber containing air to vacuum pump. So they are pumping out the air until vacuum becomes inside. A student hears the bell ringing. The air is then removed from the chamber. State and explain the change of the sound. Of course, since the particles are getting less and propagation of sound wave depends on the particles, it moves from one particle to another. So the sound will get lower and lower until when it's totally vacuum inside and all the air is pumped outside, you will never hear any sound. So the air is removed, so no sound is heard since there is no medium anymore. And sound waves do not propagate in vacuum. Number 6. Figure 6.1 shows an object O placed in front of a plane mirror M. Two rays from the object to the mirror are shown. Part 1 on figure 6.1. For one of the rays shown, draw the normal to the mirror. So we need to make a right angle and draw our line. Just be perpendicular to the plane. We can also extend it from the other side. This is the normal. And now mark the angle of incidence and label this angle. Angle of incidence is between the incident ray we chose and the normal, and we call it I. And we call it X. To I on figure 6.1, draw the reflected rays for both incident rays and construct the lines to locate the image O. Label this image I. So we need to draw the same normal for the other line, which is clear in this case to be the vertical. Now we need the protractor. Angle of incidence can be measured to be around 65 degrees. So the first angle is 65 degrees, and so we take 65 degrees from the other side. Now we put this axis on the normal and measure 65 degrees from the other side. This is for the first angle. For the second angle, do the same process. Now we move the line, the protractor, to the second line, and we measure the incident angle, which is in this case 45. So we move the axis to the normal and measure 45 from the other side. Now we draw the reflected ray for the first one, and then the reflected ray for the second one. They should intersect at one point, which should be the image of O, and opposite to it. So the intersection between these two lines is I, which is the image of O with respect to the mirror. Part B. In figure 6.2, circular wave fronts from a point source in a tank of water strike straight barrier. The reflected wave fronts seem to come from a single point. On figure 6.2, mark a dot to show the position of this point. Label this point C. This point is actually the image of the source with respect to the barrier. It should be at the same distance, which is 2 centimeters. So the image is 2 centimeters from the barrier as the source, and the line joining the source and its image is perpendicular to the barrier. 2I. Draw as accurately as possible the reflected circular wave fronts. The reflected wave has the same wavelength as the incident one, so the distance between the reflected arc should be the same as the incident. We have to adjust the radius of each circle first, make it the same length. Then we start from the barrier. We draw our first reflected circle, and then we double the distance for the second circle. 2 are enough since 2 marks are given, but we can make more if we want. Three times the radius now, and we draw the third one. So the distance between the reflected circles or semicircles is the same and equal to the distances between the incident circles, and this means that the wavelength remains the same after reflection. Number 7. A small cylindrical compressed helium gas is used to inflate balloons for celebration. In the box below, sketch a diagram to represent the arrangement of helium molecules in a balloon. Helium is a gas, so the particles are distributed randomly, and also their motion is random. They are bouncing with each other and with the walls of the container. State and explain how the size of the attractive forces acting between the molecules of a gas compares with the size of attractive forces between the molecules of a solid. In gases, or the attractive force between molecules is much less than in solid molecules, and that's why the gas molecules move freely, but in solid they are kept fixed next to each other. The helium in the cylinder has a volume of 6 times 10 to the power negative 3 meters cubed and is at pressure of 2.75 times 10 to the power 6 Pascal. The pressure of helium in each balloon is 1.1 times 10 to the power 5 pascals. The volume of helium is inflated in the inflated balloon is 3 times 10 to the power negative 3 meters cubed. The temperature does not change. Calculate the number of balloons that were inflated. So we have to find first the volume at the new pressure. So this is the volume at this pressure, and now the pressure is changed to this value. We have to find the new volume of helium. The new volume we find is the total volume of helium, and this is the volume of helium in one balloon, so we divide them by each other. We know that pressure is inversely proportional to volume. This means P1 V1 is equal P2 V2. So 2.75 times 10 to the power 6 multiplied by V1, which is 6 times 10 to the power negative 3, is equal P2, which is 1.1 times 10 to the power 5 multiplied by V2. This means that V2 is equal this quantity divided by this quantity, and it will be 0.15 meters cubed. Number of balloons will be the change in volume, which is 0.15 minus 6 times 10 to the power minus 3 divided by the volume of helium in one balloon, 3 times 10 to the power minus 3, and the answer will be 48 balloons. Later, the temperature increases and some of the balloons burst. Suggest and explain why this happened. Why the balloon burst. Temperature is directly proportional to pressure, so as temperature increases, pressure also increases. So more pressure, which means more collision of the gas molecules with the walls. So molecules move faster and collide more with the walls of the balloon. Number 8. A charger for a cell phone or mobile phone is marked input AC 240 volt, 50 Hz, and 80 milliampere. The output is DC 5.3 volts, 500 milliamperes. State the component in the charger that converts AC to DC. It is actually a rectifier responsible for changing AC to DC, and it's made mainly of diodes. The quantity that has the value of 50 Hz, Hertz is the unit of frequency, of course. Calculate the output power of the charger. P is equal to voltage multiplied by current, which means 5.3 volt multiplied by current, which is 500, and since it's milliampere, so we multiply by 10 to the power negative 3 to make it in ampere, and the answer will be 2.6 watts. The energy transferred in the output circuit when the cell phone charges 1.5 hours, the energy transfers in the output, so E is equal P multiplied by T, which is equal to 2.6 watt multiplied by 1.5 hours changed to second multiplied by 3600. Now we get in second. The answer will be 14,000 joules. In the following list, underline the quantity that is stored in the battery of the cell phone. Cell phone stores only electrical energy. Voltage is not stored. We say that energy is stored at a certain voltage. Current is also not stored. Current is the flow of charges. So we say current when the charges flow, not being stored. And power is energy per unit time. We're talking about total energy, which is the only answer. Number 9. A technician sets up a radiation detector in a university laboratory for use in some experiments. Even before the radioactive source for the experiment is brought into the laboratory, the detector registered a low count rate. Suggest what causes this count rate. This is due to the background radiation, of course, since there are radiations around us everywhere. Maybe rocks, maybe buildings, building materials, etc. A radioactive source that emits alpha particles is placed on the laboratory bench, and the source is gradually moved closer to the detector. At first, the detector continues to register a low count rate, sometimes slightly less than the count rate registered without the source. The count rate suddenly increases to a very high value when the source is very close to the detector. Explain these changes in the count rate. When the count rate was very low, this means that it was due to background radiation only. Now, when the reading were slightly less, this is because radioactivity is random. So even the background radiation may change and fall down sometimes. So we may record later a value which is smaller than the value recorded previously. When the reading is very high reading is due to alpha particles emitted from the source, and each one for 1 mark. Part C. In a second experiment, alpha particles pass between two parallel horizontal metal plates in a vacuum. They then continue to the detector as shown in figure 9.1. A positive charge is established on the upper plate and a negative charge on the lower plate. On figure 9.1, sketch the new path of alpha particles. Now, alpha particles are positive, so they will be repelled by positive and attracted by negative, and so they will follow a cursed path downwards. State what happens to the count rate registered by the detector. Of course, it decreases because most of the alpha particles will move away from the detector. So, count rate decreases. Actually, all the alpha particles will move away, and so detector will read the background radiation only. To background radiation. Number 10. In a room in a house there are 4 electric lamps in parallel with each other controlled by a single switch. With all the lamps working, one of the lamp filaments suddenly breaks. What, if anything, happens to the remaining lamps? Explain your answer. First of all, the lamps remain all of them on since they have independent branches. All of them remain on and have the same brightness. Nothing happens for them. Same brightness. It's enough to say that nothing happens, 1 mark for this, and then since you state the reason, since they are connected in parallel, 1 mark for this sentence. Figure 10.1 shows a circuit diagram for a lamp in another room. X and Y are two-way switches. Complete the table by indicating whether the lamp is on and off for each of the switch position. First position, switch of X is on position 1 and switch Y is at position 1 as well. This means that there is a complete path, so the lamp is on over here. Now 1 and 2, 1 and 2, so this means that there's no current over here. So current will reach here and stop, and there is also an opening over here, so it's off. 2 and 1, same. 2 means like this and stop here, and 1 means like this, so it won't be working, so it's also off. Now 2 and 2, so it will be on. Explain why this arrangement of switch is useful. The advantage over here is that we can control the switch from 2 positions, from here or from here. Turn it on and off from here according to this position. So if these two switches X and Y are very far from each other, I can control the lamp from this position and from this position in case the lamp was very far. So the answer is controlling the lamp by 2 switches. When I change the state of any switch, whether this or this, the state of the lamp will change. It's depending on 2 switches. Finally, question number 11. Name the process that causes a potential difference across the solenoid due to the movement of nearby magnet. This is called electromagnetic induction. The word induction alone is not enough. That's why this is underlined in the mark scheme. Electromagnetic. Figure 11.1 shows the solenoid connected to a center 0 voltmeter M. A bar magnet is held with the north pole close to one end of the solenoid. The magnet is pushed into the solenoid and then brought to rest with its N north pole just inside the solenoid. Describe the movement of the pointer of the meter. We have to say that the pointer deflects. We don't know in which direction, but deflects while the magnet is moving and then returns to zero when the movement of the magnet is stopped. The magnet is now pulled to the left. The magnet is now pulled to the left out of the solenoid at a high speed. Compare the movement with the pointer of the meter with that seen in I. Since now left means opposite direction, so pointer deflects in the opposite direction, and since higher speed, so it will deflect faster since the current depends on the speed of movement, so and returns to zero in a shorter time. That was the last question in the test. Thank you very much.